on the book. Look at this one, 1.7. Prove that modulus of z1 plus z2 is less than equal to modulus of z1 plus z2. So there are different types A, B and C. So we'll start with the A. So I'll just show you how to proceed with this. Perhaps you already know it, but then let us see. First of all, what is modulus of a complex number? You know that it is equal to x squared plus y squared if z is equal to x plus iy. So this is what you know. So let us look at this one where they have asked us to prove that z1 plus z2, the modulus of z1 plus z2 is equal to, it's less than equal to modulus of z1 plus modulus of z2. So to solve this, what we do, let z1 is equal to x1 plus I y1. Then we go to z2 is equal to x2 plus I y2. So obviously from here we know what is z1 plus z2. Therefore z1 plus z2 is equal to, when we add this plus this, what do we get? We get here, we can write it in the complex number form like this, x1 plus x2, which is the real part, plus I into y1 plus y2, which is the complex part. So what is z1 plus z2? z1 plus z2 is obviously equal to modulus of this which is root over x1 plus x2 whole square plus y1 plus y2 whole square, like this. Now this is this one, and what about the other part? Other part is quite simple because it will be just x1 square plus y1 square and plus x2 root over x2 square plus y2 square. So if this is true, if z1 plus z2 is less than equal to this plus this, then how will I write? Then when I open it up, this becomes root over x1 plus x2 whole square plus y1 plus y2 whole square is less than equal to modulus of z1 is what? It is root over x1 square plus x2 square plus modulus of z2 is, so I'm so sorry, this should be x1 square plus y1 square. So this should be plus y1 square, and this is x2 squared plus y2 squared. So this will be this much. So let me clear the board and go to the next step. So I'm sure you must have noted down because I'm rubbing it off. So in the next step, let's square both sides. So when I square both sides, what I have is squaring what I have, the root over goes off and we have x1 plus x2 whole square plus y1 plus y2 whole square, which is less than equal to, we have to open the whole by a plus b whole square formula, so that we have here x1 squared plus y1 squared plus twice x1 squared plus y1 squared into x2 squared plus y2 squared plus x2 squared plus y2 squared. So this is what? This is x1 squared plus x2 squared plus twice x1 x2. We're just opening by the a plus b whole square formula. So again this is y1 squared plus y2 squared plus twice y1 y2, which is less than equal to all these. This is again x1 squared plus y1 squared plus 2, so will I write it this way, plus twice, I already have a plus, so plus twice x1 squared plus y1 squared multiplied by x2 squared plus y2 squared. So I can put the both of them inside the bracket, inside the square root, because it's the product, plus x2 squared plus y2 squared. So you see x1 square goes off with x1 square, x2 square goes off with x2 square, y1 square goes off with y1 square, and y2 square goes off with y2 square. That implies twice x1 x2 plus twice y1 y2 is less than equal to 2 times of, so you see the 2 will also go off, x1 squared plus y1 squared multiplied by x2 squared plus y2 squared. So this is like this, and so we have this which will go off, and let's square it again, because I want to remove this square root on the right hand side. So this, when I square both of them, what do I get? I square on this side and on this side. So what I get? I get x1 square x2 square plus twice x1 x2 y1 y2 plus y1 squared y2 squared is less than equal to x1 squared plus y1 squared multiplied by x2 squared plus y2 squared. But then you have to multiply this on this part, which becomes x1 square x2 square, which of course will go away with this one, and similarly I'll have a y1 square y2 square, which will go off with this one. And what I can do is straight away I can put only the terms. From here I'll have twice x1 x2 y1 y2, because these two terms will go away with the corresponding terms this way, is less than equal to x1 square y2 square plus x2 squared y1 squared. So we have this, and like this. Now this is equivalent to, if I can take it to the other side, what this becomes is that we can write this as, let me clear the board. I can write this as that implies x1 y2 minus x2 y1 the whole squared actually, which is greater than equal to 0. But we know that this is true because this is what? This is a square, complete square, and so this has to be greater than equal to 0. So we had assumed the relation that is given and we found something that is true, which means that z1 plus z2 modulus of this is less than equal to modulus z1 plus modulus z2. So this is one thing, and this is how you prove this kind of things, and we can certainly do the other numericals from here. Now let us look at some other type of numerical. These are very similar, the ones we are doing. So to express in, let us see how we can express in terms of in the polar form. That's what I wanted to show you. I wanted to show you a numerical where you can put it in a complex form. So we have one of them, I think. Well, I can't even find it here. Yes, polar form. So express, look at 1.1.6. Express in the complex these following numbers in the polar form. So let's see how this can be done. So the first example is to find 2 plus 2 root 3i they have asked, and they have asked us to express this complex number in the polar form. And polar form we know in terms of r and theta. So what we do is we write this as r cos theta plus r I sin theta, which is equal to how do I find r from here? We know what is r. We know that r is equal to root over, because this is in the form x plus yi, and what is r? R is x squared plus y squared, which is equal to how much? X is 2, so it is 2 squared plus y is 2 root 3, so it is 2 root 3 square, and this gives the answer to be root over 16, which is 4. So we get r is equal to 4. This we get, and now we set out to find what is. We know that y is equal to r sin theta, isn't it? Because you see, this is y, and this r sin theta. That implies what is sin theta? Sin theta is equal to y by r, which is nothing but root 3 by 2, which gives theta to be is equal to 60 degree, which is equal to pi by 3. So I can write it in the polar form as 4 cos theta plus 4 sin pi by 3. This both will be pi by 3. This is done, so you can look at it. So I must stop here.